Hello everyone, welcome back to Intelligent Machines. I'm Dr. Mohan, PhD in Industrial Computer Science and Artificial Intelligence. In this video series, we are exploring how diffusion model work, especially in image generation. In the last video, we trained a model to generate handwritten digits using MNIST dataset. We implemented one version of the unit from scratch in PyTorch and another using Diffusers library from Hugging Face. From now on, we are going to stick with the Diffusers library because one main goal of this series is to help you become comfortable using it for real projects. So in today's video, we're going to do something really exciting. We'll train a diffusion model to generate celebrity faces from random noise, something like this. You might have seen images online that look pretty real, but the people in them do not actually exist. We are going to build something similar today. For this, we'll use a publicly available dataset from Hugging Face, which contain around 10,000 celebrity face images. Each image also comes with a gender label, one for female and two for male. We'll use this label during training so that later we can tell our model generate a male face or generate a female face, depending on the input label. However, one small note, will not generate very high resolution images. We'll stick with 64 cross 64 pixels to keep the training faster and more stable. Also, instead of using all the 10,000 images, we are going to take only 1,000 images. All the codes that we are going to see today are already present in my GitHub. You can go to the part 3 diffusion select faces and this particular notebook and you'll be able to find them. Now let us go step by step. First, we import all the necessary libraries, very similar to what we did in the previous videos. Then we load our dataset using datasets libraries load dataset function. It allows you to easily download dataset directly from Hugging Face Hub. After doing that, we only keep 1,000 samples and then we filter them using gender 1 and 2. There are a few samples with other gender values, but keeping them breaks the unit embedding setup since our model expects only two class embeddings 0 and 1. And this is how a single sample look like. So it has different things like whether it is an adult, many parameters, but we are only concerned with gender and the image. The image is basically a pillow image. And here we showed the 100th image and it looks something like this. We next perform the standard pre-processing steps, resizing to 64 cross 64 pixel and transform into PyTorch tensor, then normalize to have mean 0 and standard deviation 1. Then I create a small helper function like this that applies this transformation to each sample. Once we do that, we can see that, so this is where we do the transformation to all the samples. We run this. And after doing the transformation, we can see that each sample now has an extra field called pixel values, which stores the image tensor now. This is exactly what we need for training a diffusion model. Now we define a very simple collate function for creating the batches. Although our images are of same size, we still use a custom collate function to adjust the labels. Since the dataset labels are 1 and 2, but the model expects 0 and 1, we subtract 1 from each label. Now we have our data loader ready with batch images and labels. And this is how one batch of images looks like. It has four images per batch, and this is their corresponding label. Now we'll go to the diffuser setup. First is the scheduler. We're going to use the DDPM scheduler. This is the beta start, beta end, the linear scaling, and number of time steps we're going to use, which is 1,000. And after that, we're going to do a simple forward pass. As before, we sample the noise, add it to the image using current time step, and observe how the image becomes noisier over time. This forward process is what the model will learn to reverse. Now we initialize the unit. This time, instead of one input channel, we have three input channels because we have RGB images. The number of class embedding is 2 because we are training on male and female faces. When we print the model summary, we see it has around 17 million parameters. And to do a quick sanity check, we do a simple forward pass through the model by generating random input, random time step, and random labels, and it runs fine. Before starting the training, let us create a generate function so that we see that how our imaging is being generated during the training process. We generate a small batch of 4 images with label 0011. This means the first two should be female faces and next two should be male. For instance, we use the DDIM scheduler here, this one, which lets us generate image in fewer steps. For example, just in 50 inference steps, though in the training we are using 1000 steps. We'll talk more about how scheduler like DDPM and DDIM differ in an upcoming video. During the generation, so here is the generation. During the generation, we start from pure noise, which is this one. In each step, the model predicts how much noise that needs to be removed, and using the scheduler, we do the reverse diffusion process, and this is the less noisy image. Gradually, as the steps progresses, the image becomes clearer until we finally get a clean sample. If we run this generate image before training, of course, everything looks random, just noise. But after training, we'll start seeing some real phases. Now let us move to the training part. First, to initialize our loss function and optimizer. Here we are training for 50,000 steps. For each batch, we get the pixel values, which is the images and the corresponding labels. We sample random noise and time steps and use those random noise and time steps to corrupt the images and get the noisy value of X. And then we pass this noisy X to the unit, and unit predicts how much noise that needs to be removed. We calculate the loss between predicted noise and the true noise that was been added. Then we backpropagate and update the model weights. Every 500 steps, we save some generated samples to visualize the progress. I have wrapped everything that we saw there in this train faces.py file instead of Jupyter Notebook so that the training runs smoothly and saves intermediate outputs to a folder named runs. And there you see, so this is the image after the generation, after 1000 steps. We see some colors. It's not entirely random now. After 10,000 steps, we really start seeing some facial structure, and we can see that it respecting our labels. That means the bottom two are male and top two are females. After 2000 steps, the facial outlines become clearer, and around 40,000 steps, you start seeing clear pictures. I think one of them looks like Brad Pitt. I think one of them looks like Brad Pitt. Let me know in the comments if you think so. So that was all about today's video. We successfully trained a diffusion model to generate celebrity faces from random noise using diffuser library. In the next video, we're going to explore something even more fun, which is image inpainting using diffusion model. If you do not know inpainting, it is when you take an existing image and edit or replace a specific region using a diffusion model. For example, we take a portrait of, let's say, Donald Trump, and we want to change his hairstyle. So for that, we'll mask the upper part and use the diffusion model to generate different hairstyles. So you see this one looks pretty accurate to me, this one or this one. If you enjoyed this video, do not forget to like, share, and subscribe to Intelligent Machines. Share it on LinkedIn or with your friends who love AI. And if you have any suggestion or question, drop them in the comments below. Until next time, stay curious.